Okay. So we discuss about the Mohr circle for stress for the stress value. Now we need to discuss about the Mohr circle for strain. Note down. The next concept will be Mohr circle for strain. So till now in the GATE examination, they have not asked about this Mohr circle for strain. They have touched the part called Mohr circle for stress value, but they have not asked about the strain. So that is what we are going to see. Now for Mohr circle for the strain value, Mohr circle for strain. See, Mohr circle for the strain here, the y-axis and x-axis that will be different. That will be different. Here the y-axis will be gamma by 2, and here x-axis will be strain. Please note down. See, so whatever the normal stress on any oblique plane, normal strain on any oblique plane will be x coordinate of Mohr circle. Very important, please note down. Now, whatever the y-axis is there, that is nothing but shear strain. So suppose you want to calculate the shear strain on any oblique plane, that you can just calculate it by y coordinate of Mohr circle. Y coordinate of the Mohr circle. That means, I think you know the formula, tau is equal to what? G into gamma xy. That same formula I'm talking about. Here where gamma xy is what? Shear strain value. Yes or no, guys? Suppose a block is there. Suppose block is there. Now we apply the shear force, something like this. You know that the block will displace like this by the amount phi. This phi value only we calling what? Shear strain. Understanding or not? This phi value only we are calling what? Shear strain. Understanding? Please note down. This is nothing but y-axis will be shear strain by 2. But remember, we need to multiply with the what? 2. Because here gamma xy by 2 is there. If you want to get the shear strain, we need to multiply with the 2 value. That's it. Note on the sign convention, that is also very important. Sign convention that we need to look. Suppose your coordinates are coming something like this. P coordinate is coming where it is having some normal strain and where it is having some shear strain. These coordinates are there. For point P, what we can write? For point P, what is the sign convention we can write? It is positive and it is what? Like this. So what we can write? Note down. Normal strain, whatever represented at the position at the point P, that will be tensile. gamma as theta, whatever we have represented, that is clockwise. Note down, that is clockwise. Very important. Now, sir, what is the formula for normal strain at an angle theta, and what is the shear strain at an angle theta? That also we need to, check it out. That is again very easy. Whatever the formula you have seen, for normal stress for any oblique plane, the same formula will be there. Little bit of difference will be there. That we are going to, that thing we are going to discuss. Now, once it is done, let me know. This particular portion has not covered till date in GATE examination. Single time also they have not asked about this. So this is nothing but y-axis will be shear strain by 2, and this is nothing but normal strain. Note down the formula for sigma and theta, or sorry, epsilon and theta. That's a very easy formula. And again that sign can, whatever the formula I'm telling to you, this formula will be valid when you follow my sign conventions. So epsilon x plus epsilon y by 2, epsilon x epsilon y by 2 cos 2 theta plus gamma xy by 2 sin 2 theta. It's a very simple. Same formula is there. Instead of tau, replace tau with what? Gamma xy by 2. Tau xy replace gamma xy by 2. That's it. That's only the difference will be there. Nothing much is there. Right? So note down. This is the first formula. And the second formula, you know that tau is there. So it will be gamma s by 2 theta. That will become epsilon x minus epsilon y by 2 into sin 2 theta minus gamma xy by 2 cos 2 theta. So this is the first equation we are going to have. And this is what I'm going to have the second equation. That is one of the very, very important thing. And again, I'm going to say sigma n theta plus sigma n theta plus 90. Together, summation will be what? Epsilon x plus epsilon y. Very, very important, guys. And again, principal strain and principal, major principal strain and minor principal strain value, you can calculate by using same formula. Major principal strain and minor principal strain you can calculate by using this particular formula, which I'm telling you right now. Epsilon x plus epsilon y by 2 plus minus under root of epsilon x minus epsilon y by 2 whole square plus gamma xy by 2 whole square. That is one of the very, very important thing. Note down, guys. And again, epsilon 1 plus epsilon 2 will be equal to what? Epsilon x plus epsilon y. Anybody know about the matrix, stress matrix and strain matrix? What do you mean by stress matrix and strain matrix? That we are also going to discuss about these things. Now, once it is done, let me know. Done, all of you? Perfect. Perfect. Now, so here, with the help of this question, we will try to understand the stress matrix first of all. So whenever I'm going to write 3D stress matrix, sigma xx, sigma yy, sigma zz. tau xy, tau xz, tau yx, tau yz, tau zx, tau zy, tau zz. This is nothing but 3D stress matrix we call. In this one, my dear friend, this is nothing but what? Totally x phase, totally y phase. This is what about totally z phase, right? This is what in this column, if you just move like this, if you just move like this, so it is nothing but what? X direction, y direction, z direction. First of all, you need to understand what is the meaning of sigma xx. Let me just show you by cubical element. Let me just show you by the cubical element. So in this cubical element, my dear friend, if I want to show sigma xx, what is the meaning of sigma xx? Suppose this axis, suppose I'm taking this axis to be what? Just wait. I'm taking this axis to be x axis. This axis to be y axis. And this axis to be what? Z axis. This particular phase is what? The first letter is showing that. The first letter is showing is what? The phase. The second is showing what? Direction. X phase, X plane, or in the, we can say that XY plane, or simply you say whatever the axis will be there, that will become phase. X phase, X direction. Now suppose I want to show you sigma YY. Y phase, Y direction, sigma YY. Z phase, Z direction, something like this. Suppose I want to show tau XY. How it will look like? X phase, Y direction, X phase. It should be in the X phase, but in the Y direction. This will be your tau XY. Understanding my point or not? Check it out, guys, all of you. Suppose I want to show you tau ZY. How we can show tau ZY? Z phase, Y direction, Z phase, Y direction. Z phase, Y direction. Understanding my point or not? Tell me, guys. Yes? All of you are getting my point? Correct. In this particular question, my dear friend, the question which I am showing you right now, in this question, they are asking the state of stress they have mentioned by what? By the matrix, and they are asking what will be the center for the circle. You know that this is the 3D stress. If I just show you 2D stress, this thing will be gone. This thing will be 0 for 2D stress. So what will be the condition? Sigma xx, tau xy, tau yy, tau yx, and sigma yy. This will be my condition for 2D stress matrix, right? Now, in this question, they have given sigma xx to be 20 megapascal, sigma yy to be what? 20 megapascal, tau xy, and of course tau yx. Both will be same, and both are equal to what? 0. They are asking center for the circle. What is the center for the circle? You know that I mentioned in the formula yesterday lecture, sigma x plus sigma y by 2 comma 0. Now 20 plus 20 by 2, that means 40 by 2. 40 by 2 is what? 20, 20 comma 0, that will be the center. What will be the radius? What will be the radius? Radius is nothing but what? Radius of Mohr circle is nothing but what? The radius of Mohr circle is nothing but tau maximum. And how to calculate the tau maximum? How to calculate the tau maximum, guys? Sigma 1 minus sigma 2 by 2, right? Yes or no, guys? 20 minus 20 by 2, that will become what? 0. So which option will be correct? So I can represent this stress matrix to be something like this also. Like this also. Getting my point, all of you? And just note on the coordinates 20, 0. P is what? 20, 0. Now if you draw the Mohr circle, A and B both are coinciding. Both are coinciding. Take the midpoint, draw the circle. It will become points only. So somebody will ask you the Mohr circle for this case. This will become point. The point is not going to have any radius. It will have 0 radius, but the center will be what? Exactly 20, 20, whatever the unit will be there. At that distance, center of the circle will be there. Understanding my point? Tell me, guys. All of your understanding? Or any confusion? Okay. So we have done with the Mohr circle and this one. Now let's focus on the torsion chapter. The next chapter will be torsion that we need to finish. Now once it is done, let me know. Done, all of you? So you have so many methods, analytical method, graphical method to solve the problem of what? State of stress. State of stress means minds of the stress at the particular point. In a particular material, lot of points will be there. All the points, how they are feeling, how much of stress they are feeling, that can be represented. See, somebody's feeling can be represented by what? By its face. The same thing is going to be with the what? Material also. And that particular thing representation will be done by either you can just represent by matrix or you can just represent by Mohr circle. We have the many methods to allocate those particular feelings of that particular point. How much of stress they are feeling, whether they are feeling only in the x direction or they are feeling in only y direction or they are feeling in only z direction or they are feeling combined with all the directions. That's things. That is called as complex state of stress. Now, note on torsion of the circular shaft. We don't have torsion of non-circular shaft. That is the first thing. So the next chapter will be the torsion of the circular shafts. So before discussion of those things, just note on this diagram. One of the very, very important torsional stresses and strain. You need to understand two things, theta and phi. So what is the meaning of theta? What is the meaning of phi? That first of all we need to understand. Whenever there is a circular shaft which is having a length L and diameter D, when it is twisted, try to imagine the 3D figure of the twisting. When we are going to twist this one, then there might be some angle of twist and there is some shear angle. There will be some shear angle. Of course, that I am calling to be what? Shear strain. But there is a there will not be that much similarity between theta and phi. That we are going to see. So first of all, note on the terms and terminologies. Theta is nothing but angle of twist. Angle of twist of the cross section. Phi is gonna be shear angle. Shear angle on the surface of the shaft. Shear angle on the surface of the shaft. Now, the shear angle on the surface of the shaft. So first of all, note on this figure. This figure is very, very important. I'm going to take one more section. I'm going to take one more circle, something like this. And from here, I'm going to represent, I'm going to take, or let me not confuse you. I can take somewhere else also. One cross section I'm showing you, this one at the free end. Other cross section, let me take at a distance of L1, suppose. Now in this case, what will be my conditions? Suppose I am representing this with the what? Theta dash. And this I'm taking at a distance of, L dash. Right? Now tell me, the phi value is same for L dash and L or different? Tell me guys, try to imagine the figure and let me know the answers. So try to focus on this triangle. C A dash. Triangle C A dash. Now if you focus in this particular triangle, what is the tan phi? This arc divided by what? Length. A dash divided by what? Length. A dash divided by what? Length. What is the A dash? Can I say R into theta? If R is the radius, can I say R into theta divided by L? Check it out. If phi is very small, we can say 10 phi will be equal to what? Phi, and then phi will become what? R theta by L. Check it out, guys. All of you, please check it out. Yes or no, guys? Please check it out. Correct. Now, just focus. We got some relationship between shear angle and the angle of twist. We also got some relationship between phi as well as radius. Phi as well as radius, we got some equation. Now, so whatever this angle is there, at this particular cross section, either you take or this particular cross section, the phi value is going to be same for both. The phi value is going to be same for both the case, my dear friend. Are you understanding? Whatever the angle is there, this angle will be same for this cross section and this cross section. Yes or no, guys? The angle will be same, right? Either you take a distance L dash or you take a distance L or you take a distance L. The angle will be same, right? Yes or no, guys? The angle will be same. Check it out. All of you, please verify it. Whatever the phi is there, that is going to be same for the section which I consider at a distance L dash from the fixed end and L from the fixed end. So we can say that, what we can say, L dash is less than L, but phi, what we can say, suppose phi dash will be equal to phi. So note down here important point, the shear angle will be independent of the length of the shaft. That is the very first point. Please note down. The shear angle will be independent of the length of the shafts. Now, let me show you one more diagram. Just wait. Now let me show you one other example. Suppose I'm taking the shaft. which is fixed at one end, and the other end is being extended, something like this. The other end is being extended, something like this. And now we have applied twisting. Now we have applied twisting from the center. Let me just take this section like this. And what we can draw, just wait. A very first section I'm going to consider is something like this, where this angle is what? The angle of the twist will be, suppose, theta. The angle of twist, suppose theta, and angle of shear angle will be what? Suppose phi. Now let me take one more section. Let me just take one more section from here. Yes. Sorry, just wait. I think I can take points something like this: X, Y, Z. X, Y, Z, I'm taking the points. Now, guys, now try to understand X, Y, Z. All the points I have taken. No, I cannot take at this point. See, just wait. Let me draw the figure actually. Somewhat big figure. One end is fixed one end is fixed one, and other end is what? Is free end, where the twisting has been applied. Where the twisting has been applied, my dear friend. Now, what I'm taking one section over here. You know that the angle of twist will be 0 for this case. Angle of twist at the fixed stand will be 0, right? Angle of twist at the fixed stand will be 0, right? Because it is fixed one. It cannot come out from the support. Yes or no, guys? It cannot come out from the support. Yes or no, guys? Suppose the shaft has been twisted from here to here. Suppose the shaft has been twisted from this location to this location. Then what is going to be happening? Suppose the shaft has been twisted by the angle theta. Check it out. All of you, please check it out. Understanding or not? Now, let me draw the figure. The things will be clarified. Let me first draw the figure actually. What actually I want to say is that with this figure, it will be clarified. Try to focus. Try to focus, my dear friend. Here, let's suppose this is phi dash. Here, let's suppose it is phi. Try to understand. 2 to 3 things are very important. The conclusion which I'm going to make through this particular figure. Now, let me give the point also C1, C2. C1, C2. Let me give the 2 points. C1, C2. Try to understand the angle of twist which I mentioned you, and let me consider the point. Suppose point I'm going to take X, Y, Z. 3 points I'm going to consider at the radius smaller. At the radius smaller, see, capital R will be the radius of this particular circle. The radius of circle will be what? A radius of shaft will be R, but this is nothing but small r. At that particular small radius, I'm taking the 3 points X, Y, Z. Now tell me, phi X and phi Y and phi Z will be equal or different? Or we can just write dash, dash, dash. If I just talk about the phi dash, whether it is same or different. See, whatever the point X, Y, Z you have considered, you can consider the length also different. You can consider length to be Lx. For this case, you can consider the length to be Ly. Length is different, but they are at the same radius. The length is different, but all the points X, Y, Z I am taken at all the same radius. That means radius for X, radius for Y, and the radius for Z will be same. My different phi dash X, phi dash Y, and phi dash Z will be same. Because of this. No, guys. Very first conclusion. The shear angle will not be what? Different. The shear angle will be same for all the points. But what will be the angle of twist? What will be the angle of twist? Whether it will be different or it will be same. That's a very important point, guys. You know the torsion equation, T by J, tau by R, G theta by L. G theta by L. For constant torque, for constant polar moment of inertia, for G and L, theta will be what? If you just equate these two equations, T by J will be equal to what? G theta by L. So from here, theta will be what? Directly proportional to what? Length, my dear friend. From this one, theta is what? Directly proportional to length. And you know that Lz is more than Lx. Sorry, Ly is more than Lx. So theta will be what? More for Z particular cross section, then the Y, then the X. Very see. At x equal to 0, the angle of twist will be 0. But as you keep on moving from the fixed end, your angle of twist will keep on increasing. Understanding my point? Your angle of twist will keep on increasing, my dear friend. All of you are getting my point or not? I can show you also. Let me just show that. Suppose you are going to consider this particular radius. This will be the angle of twist for theta x. That will be lesser than theta y. That will be lesser than theta. No, least one will be what? Theta x only, because it is more affected with the what? Fixed end. The moment you keep on moving away from the fixed end, your angle of twist will be what? Keep on increases. Understanding or not? All of you are getting my point? Little bit complication is there, but it is very easy topic, all I can say. Right? And from this relation also, From this relation also you are just getting what? Angle of twist is what? Directly proportional to length. So note on second conclusion. Second note, angle of twist will depend on the length of the shaft. Note on guys, very important. That thing I can clarify with the more figure. See. I know that some of you cannot be able to digest. You are able to digest with respect to this particular formula, but with the figure, it is very complicated. So let me show that. Now, try to see. How the angle of twist will depend on the length. Let me show that. These things are very important, guys. Knowing the formula, getting the answer is not at all a very difficult task. Believe me. Now, suppose I am taking at this distance, same distance I'm taking, drawing the one horizontal line. I'm drawing one horizontal line and I'm taking a distance from here. Now I'm drawing one more line, something like this. Like this. Now guys, try to understand the development of this particular figure. Now I'm taking one more cross section, something like this. Suppose here I'm taking. And let me know whether you have understood the things very correctly or not with respect to the figure which I am showing you right now. With the figure, you should be able to get the answer what actually I was trying to say. Now tell me guys, which angle will be more? Theta 1 will be more or theta 2 will be more? Tell me guys. This is fixed one. For the same shear angle, I'm not talking about the different shear angle. I'm just taking the same shear angle. Shear angle is going to be same, but for the same shear angle, you know that r theta by L. For the same shear angle, you know that r theta by L. From here, theta will be what? L into phi by r. L into phi by r. That will be the conditions. In fact, I'm taking the same radius. In fact, I'm taking the same radius. In fact, I'm taking the same shear angle. Both the things are same. See, I'm taking the points on the same particular radius. I'm not changing the radius, guys. Suppose radius is what? Same. I'm not changing the radius. I'm taking what? Same radius. But for the same radius, for the same phi shear angle, theta will be what? Directly proportional to L. When L is more, shear angle, angle of twist will also be more. So theta 2 will be more than theta 1. Theta 2 will be what? More than theta 1. Note it down. Very, very important. In fact, it's a 3D figure. 3D figure will be more clarified that theta 2 will be more as compared to theta 1. For the same shear angle. I'm not talking about the different shear angle. That is the point. But if I take the different radius, suppose at this radius, I'm taking at this radius right now. Right now, I'm taking at this radius, C radius. If I take at G radius, what will happen? If I'm going to take a G radius, what is going to be happening? Tell me, guys. What will be the shear angle? What will be the shear angle? On the same cross section? No. See, the cross section is same for the same cross section. For same cross section, I'm just taking at the free end cross section. I'm just taking the free end cross section like this. But on this cross section, my dear friend, I'm taking the things like this. Here point C, but I'm taking at G point. At G point, what will happen? What is going to be happening? What will happen with the phi value? The phi value will decrease. Phi value will decrease. Why it will increase? The phi value will decrease, my dear friend, for the same cross section. For the same cross section, angle of twist will be same. Use this formula R theta by L. For the same cross section, theta value will be same. See, theta is same for G point, C point, and G point. Theta is same for C point and G point. Because whatever the angle of twist for this one, the same angle of twist is there for the C point also. Because they are at the same cross section. Theta is same. Theta is same. Now the length is also same. The matter will be changes with respect to what? Radius. So phi will be directly proportional to what? Radius only. Right? More and more radius, more and more shear angle will be there, right? So shear angle depends on the radius. Shear angle will depends on radius of the shaft for a particular cross section. Put a note number 3 and note down. Very, very important. Very important. Shear angle will depends on the radius of the shaft for a particular cross section. Done, all of you? Perfect. Just wait for a minute. Now, just tell me what do you mean by the pure torsion? What do you mean by the pure torsion? I told you what is the meaning of pure bending. When there is a no axial load, when there is a no shear force, that is pure and pure bending will be there on that particular some segment of the particular beam. That means say it's a pure bending. What do you mean by pure torsion? no bending, only no bending, that will be enough. Like tension or compression. Now, see guys, just wait. Pure torsion meaning, the meaning of pure torsion will be, see, let me write there itself. Pure torsion will be axial load, shear force, bending moment, all will be zero. And the twisting moment diagram will look something like this. Either positive or negative, we don't know. Understanding or not? All of you are understanding the pure torsion? Twisting moment diagram. Yes or no, guys? Please note down. Pure torsion means axial load or axial force or shear force and bending moment all will be zero. That will say that it's a pure torsion. Very, very important. Please note down, guys. One of the very important highlighted concept. Now, actually, I want to draw the diagram with perfection to show that the shear angle will depends on the radius on that particular cross section. So let me try my level best. Again, I'm drawing. Try to understand, guys. The figure which I'm drawing right now, that will be the final figure. So at the center of the rotation, you know that the angle of twist will be zero at the fixed end, and at the free end, there will be some angle of twist will be there. There will be some angle of twist definitely is going to be happening at the free end. And your shaft, suppose you are taking, you are taking suppose at this particular position. Now, when you just apply the twisting moment, your shaft will be turned out and it will be what? Rotated with this particular angle. Like this, it will be rotated. Yes or no, guys? Check it out. So from the point C to D, the twisting is going to be happening. Twisting is going to be happening, my friend. Now, let me take the point. Let me take the points. Now, what I'm doing, I'm just drawing the figure. What I'm doing, I'm just drawing the figure, something like this. So very first thing will be like this. Now let me join with this one. From C to D, the twisting is going to be happening. So it will look something like this. That is nothing but shear angle phi 1. Suppose that when the shaft has been twisted from the C point to D point, the shear angle on the surface of the shaft will be phi 1. Understanding or not? When the shaft has been twisted from the point C to D with the angle theta, the center C1, and the radius is what? Suppose R, Or let me not write here. Again, you will confuse. So let me write here. This is what the radius of the shaft. Now let me take the point somewhere here. What is the radius? What is the radius? Radius will be smaller. And let me take the point from D, or we can say E to E dash. Let me take the point E to. Now it has been twisted like this. E to E dash. Yes or no, guys? With the same angle of twist. On the particular cross section, angle of twist will be same, right? For C to D and E to E dash. For C to D and E to E dash, angle of twist will be same. Check it out. All of you, please check it out. Angle of twist will be same. Yes. Yes or no, guys? Perfect. Now let me draw the figure which I want to show you. Now connecting the dots from E point to E dash point, that will be my shear angle for the shaft, surface on the shaft, what? Like this. Now, can you see my dear friend? Phi 2 is less than phi 1. Now it's clear. When the shaft has been twisted from C to D and from E to E dash, then where the shear angle on the surface of the shaft will be maximum. Look at with your own eyes. Now, that's the figure I want to try actually. Check it out, all of you. Look at very carefully. And let me know once the figure is clear. All of you, please check it out. You can see that angle is what? Very, very small as compared to phi 1. As you keep moving away from the, if you take larger and larger radius, the larger will be the shear angle for the same angle of twist and for the same length, because both the points E and C are located on the same cross section, and this cross section is what? At the same distance. So distance for C point and E point is same by different. The point distance is not changes from the fixed end. I'm taking the same distance, same shear angle for both the points, but the shear angle will be different. A shear strain will be different for both the points, that is C and E. Is that clear? So put a note and very, very important figure. Now, once it is done, let me know. Done, all of you guys? So all of you have noted down the torsion equation, right? All of you have noted down the torsion equation. T by J divided by equal to what? Tau by R will be equal to G theta by L, where J is nothing but polar moment of inertia. Yes or no, guys? All of you. Perfect. So note down fast. And there's no rocket science. I said that you can derive this torsion equation. In fact, in GATE course, we used to derive the torsion equation, but here also you can derive. There is no doubt. What is the 10 phi? Sir, R theta by L. Phi is what? For the small radius, 10 phi will become phi, and phi will be R theta by L. Once we know this phi, that is R theta by L. Once we know this phi, you know that tau is what? G times of phi. Yes or no, guys? From the Hooke's law for the shear force, you know that tau will be equal to G into phi. Am I right? Check it out. Please check it out. Perfect. Perfect. So you can also say that from here, what you can say from this particular figure, tau will be equal to what? G into R theta by L, or you can also say that tau by R, that is equal to what? G theta by L. So you got the one clarity from here to here. Yes or no, guys? Check it out. And you also know that tau is equal to what? T into R by J. So from here, tau by R equal to what? T by J. And that is how the equation and the development of the equation of torsion equation has been proposed. Note down, guys. Very, very important. Next thing will be shear stress distribution. If somebody will ask you the shear stress, there is a two types of shear stress. Remember, one is a direct shear stress and another is what? Indirect shear stress. What will be the, suppose, sir, two types of shear stress, suppose type 1 and type 2. The type 1 will be what? What we can say about the type 1? Tell me, guys. What we can say about the type 1? When you are applying the force parallel to the cross section, because of that, there is a one shear stress. Yes or no, guys? Suppose you are applying one shear force parallel to the cross section, then also there is a shear stress. And now you are applying the twisting moment. Now you are applying the twisting moment, my dear friend. Now you are applying the twisting moment. Because of that also what? The shear stress will be developed. Understanding why I'm saying there are two types of shear stress? Check it out. All of you, please check it out. Perfect. It is very similar to what we have the normal stress. One is because of the axial stress and other is because of what? Bending stress. The similar argument will happen with the what? Shear stress also, right? Now. So now we are going to see the shear stress distribution. Suppose circular shaft is there. Now the circular shaft has been applied the twisting moment. The shear stress distribution will be look something like this. Because you know from this equation T by J equal to tau by R. So tau is what? Directly proportional to radius. The more and more radius, more and more tau value. Like this. The distribution is going to be taking the shape something like this. Right? So please note down very important figure. Note down, guys. The shear stress distribution will look something like this. The shear stress distribution. So how many types of distribution we have seen? One is the axial loading distribution. That is a what? Throughout the cross section, it will be uniform. Then we have seen the bending. Of course, this bending distribution we cannot see on the plane of the cross section. We can only see this and this in the perpendicular to the cross section. And then we have seen the distribution like this, shear stress distribution. In fact, you can write torsional shear stress distribution. This is for solid shaft. And for solid shaft, note down the polar moment of inertia, pi d power 4 divided by 32. What happened with the hollow shaft? How the distribution will look for this hollow shaft? There is a hollow one. Inside that, there is a hollow one. The diagram will look something like this. Inside there is a no material, so nothing is going to be distribution will be there. There will not be any distribution will be there. No material, no distribution of the shear stress. Understanding? That's a more important figure actually. So many times they used to ask this question, it won't start from zero. Because why it won't start from zero? Because suppose you have the tau maximum, at least you are going to have the tau minimum here also. Why? Because tau maximum by tau minimum is going to have the relationship between what? R0 divided by Ri, where R0 is the radius. Suppose if I'm drawing something like this, so this is Ri and this is going to be R0. Understanding? Check it out. So this radius I'm taking from the center, Ri, and from here to here I'm going to take this to be R0. Outer radius, inner radius. Polar moment of inertia will be pi d04 minus di4 divided by 32. Very, very important. Please note down. Once it is done, let me know. This is for solid shaft and this is for hollow shaft. Once it is done, let me know. Is it done, all of you? Done? Perfect. Now we will try to solve some of the problem. That is a very, very interesting problem that we are going to have. The question number 1. With respect to torsional point of view, the outside diameter of the hollow shaft is twice than its inside diameter. That means hollow shaft is there. With the relationship has been proposed something like this: the ratio of the torque carrying capacity, to basically that of the solid shaft of the same material and same outside diameter. That means this is a diameter that you are looking right now is for hollow shaft. Hollow shaft. And for this solid shaft, the radius is what? D naught. Whatever the diameter at the outside is there for the hollow shaft, the same diameter is there for the solid shaft also. They're asking the comparison of the torque carrying capacity of the hollow shaft to that of what? Solid shaft. They are asking. That means torque of hollow shaft, torque of solid shaft. They are asking. At least try. You know the torsional equation. Same material. That means what? G is same. G for hollow, G for solid. Both are same. G for solid. Just wait. G for solid and G for hollow. Both are same. At least try for 1 minute so that I can discuss after that. See, I can give one hint. T is equal to what? T by J equal to tau by R. So from here you can just calculate T will be equal to tau times of J by R. Tau for hollow shaft, tau for solid shaft will be tau for hollow, tau for solid, J for hollow, J for solid, R for solid, R for hollow. This is same because they both are made up of same material. That is the one thing you got to know. What is the J for hollow shaft? You know that pi d naught for 4 minus d I power 4 divided by 32. And you know for the solid shaft, pi d naught power 4 by 32. You know that the radius. See, they are asking maximum torque transmitting capacity. Then tell me for hollow shaft, what should I write? If I want to write the maximum torque transmitting capacity, that is tau into R by J. Should I write outer radius or inner radius? Here, T into R by J. In that R, I need to put Ri or R naught. Tell me, guys. R naught only, right? R naught only, right? R naught only, right? Perfect. And for hollow shaft, sorry, for the solid shaft it is R naught. For hollow shaft is also R naught. So both will cancel out once again. This will also cancel out. So what I'm writing over here, 1 minus di by d naught to the power 4 simply. You know that the relationship between d naught and di is given to you, 1 minus 1 upon 2 to the power 4. So that will become 15 divided by 16 times. The option. Yes, you are hearing, that is correcting. The torque transmitting capacity for hollow shaft will be lesser than that of the solid shaft for the same space constraint. When suppose that space is same, but suppose outer radius is same, that means space is same, but one is hollow and another is what? Solid. In that case, solid shaft is better one. Suppose space is not at all a concern for you, then hollow shaft is better. Remember like this. Understanding my point? When there is a space limitation is there, then solid shaft is better one. Understanding or not? Correct. So please note down. For the same space, for the same outer diameter, for the same outside diameter, the torque transmitting capacity, who will able to transmit more torque? That means who will able to transmit more power indirectly. So if suppose the question will be asked for power transmitting capacity also, the things must be same. But the condition is power is equal to torque into omega. Omega should also be same for both the hollow and solid shaft. Then power will be directly proportional to torque relationship, right? This is nothing but torque. Note down guys, very important. Frequently, many times. In fact, not only these two exam, many exam. I think more than 40 times. This has been repeated, this question in PSU examination. Not done. Once it is done, let me know. Now try to solve this one and let me know the answer. The maximum shear stress developed on the surface of the solid circular shaft under pure torsion is what? Maximum value has been developed 160 megapascal. Maximum value. They clearly mentioned the maximum value. The shaft, if the shaft diameter is double, then what is the maximum shear stress developed will be? You know that tau will be what? T into R by J. T into D by 2, pi d power 4 by 32. So 16T divided by pi d cube. That means for same torque, the tau will be inversely proportional to d to the power 3. Right? So they are asking tau 2 by tau 1. That is what? D1 by d2 to the power 3. Now what is the d1? The shaft diameter has been doubled. That means it is what? Tau 2 will be 1 upon 8 times of tau 1. Then what will be the answer? What will be the answer? 20, right? Understanding or not, all of you? All of your understanding? Correct. Once it is done, then let me know. Once it is done, let me know. Done, all of you? Perfect. Now try to solve this question and let me know the answer. The shear stress produced on the solid shaft is tau. The shear stress produced on the surface of hollow shaft on the same material subjected to the same torque, having the outside diameter d naught and internal diameter what? D x naught, where the x will be less than 1, then what will be the relationship they are asking? So do not worry, it's a very simple question. Do not just think that whether the option is very difficult, but it's not like that. First of all, calculate the shear stress on the solid shaft. You know that solid shaft will be what? 16T divided by 16T divided by what? Pi ds cube. Yes or no, guys? Suppose I'm writing top. What is the shear stress on the hollow shaft? What will be the shear stress on the hollow shaft? T into d naught by 2 divided by pi divided by what? 32 d naught power 4 minus di to the power 4. They mentioned clearly that di is equal to what? Di is nothing but what? Di is nothing but x times of d naught. They clearly mentioned that di is nothing but what? X times of d naught. Right? See, it is not dx naught, it is d naught into x. Understanding or not, all of you? All of you understanding the relationship that has been proposed? It is d naught into x. So now if you put into this equation, now if you just put into this equation, what you will be calculating? T into d naught divided by 2. I'm just taking pi d naught power 4 by 32 outside. 1 minus di by d naught I will be calculating to the power 4 like this. Now, tau hollow shaft will be, just look at this one. 16T divided by what? Pi d naught cube 1 minus x to the power 4. You already know that the both are subjected to the same torque and having the same outside diameter. Here d naught and here also d naught. That means this is what? D naught. So directly can I write something like this or not? Tau hollow shaft will be tau solid shaft x to the power 4. In short, hollow shaft will be tau s divided by what? 1 minus x to the power 4. Check it out, guys. Which option is correct? A. Understanding or not? All of you understanding? Little bit of correction is required. It's d naught times of x. Maybe 1 upon 2, 1 upon 4, 1 upon 3. It doesn't matter. Directly relationship has been given and directly we are calculating. So here what you are calculating? Suppose d naught is equal to what? Di. Question is complete, but I'm just moving beyond that. 1 minus 1 upon 2 to the power 4. So it is what? Tau s divided by what? 15 into 16. Now tell me, for the same torque, suppose hollow shaft and solid shaft both are subjected to what? Same torque. Which is going to be fail first? For same space limitation is there. Space limitation is same because outside diameter is same. Power transmitting capacity is also going to be same because now you have applied same amount of torque. Whatever the torque is there, see, capability of the hollow shaft is not that much to bear that much of what the solid shaft can bear, the torque. But assuming the conditions, whatever the solid shaft torque transmitting capacity is there, you just thought that hollow shaft will also have the same capacity and you have applied the same torque. In that condition, the tau value for the hollow shaft will exceed the yield stress value and it is going to be fail first because it is 16 times solid shaft. Understanding the meaning? Correlations. In the previous question, we have just come across the relationship between power transmitting capacity or torque transmitting capacity. In this question, we are looking how the failure will happen. When conditions are same, the hollow shaft will gonna be fail first. That's the reason it is mentioned that the torque, whatever the torque you are applying for the solid shaft, you just apply little bit lesser torque for the hollow shaft for the same limitation, for the same space limitation, for the same amount of material. If suppose condition has been given, material is very strong for the hollow shaft, then you can apply the same amount of torque. That's a different matter of concern, right? Now, is it done, all of you? Perfect. Now try to solve this question. A solid shaft is there. Okay, I forgot to mention about the sign convention. Note down, guys, sign convention for this twisting. Whenever at any cross section, you are having something like this. Sir, what is the double arrow? I will tell you. The twisting movement will be positive. At any cross section, suppose you are having something like this, the twisting will be negative. I will tell you, do not worry. It totally depends on the direction which we are weaving, in which we are weaving from the right hand. Suppose you are rotating your finger, where the thumb direction will be there, that will be deciding factor for the directions. Now, a solid shaft D and having a length L is fixed at both the ends. This solid shaft is there, which is fixed at both the ends. A torque T0 has been applied at a distance L by 4 from the left hand, as shown in the figure. They are asking maximum shear stress in this shaft. It is made up of two shafts, something like that, A, B, C. Just like a bar connected in series combination. Understanding or not? All of you understanding? Just like a bar connected at the what? Series combination. You know that. Note down one important point. Bars in series. Whenever bars are connected in series and torque has been applied only at the extreme ends, the torque has been applied only at the extreme ends, then TAB, TBC will be same as plus T or minus T. Check it out. Rotate your finger like this. Rotate your finger like this. In the looking from here, looking from this end, and try to rotate your finger and just see where the thumb is going, leftward or down, rightward. Leftward or rightward. Rotate your right hand finger where the thumb is going. See, for me, it's a left hand. It is going something like this or not? Check it out. All of you, please check it out. All of you, please check it out. Whether it is going some, see guys, it's a very simple. When you are applying the loading condition, twisting movement, something like this. Now you are rotating your finger in the what? Anti-clockwise direction. Then it is going like this. When you are rotating your finger in the clockwise direction, it is going leftward. That means it is plus T. Please note down. Now both the shafts will be subjected to what? Same amount of torque. And angle of twist will be theta AB plus theta BC. Note down two conditions. Same, my different, same axial loading condition what we have seen. The forces as well as deflection. Here deflection will not be axial deflection, it will be angular deflection. That is called angle of twist. When the bars are connected in parallel combinations like this, one is inside one and outside we have some other material. Both are subjected to the torque, something like this. Now for parallel combination, same, everything is same. The torque will be distributed T1 plus T2 for 1 and for 2. But angle of twist for this both the bars will be same. Understanding or not? Just like whatever the axial deflection will be same in the parallel combination, same thing we are following for the angular deflection also. Right? So this is the parallel combination. This is nothing but series combination. Check it out. All of you, please check it out. Tell me, guys. Very quickly, tell me. Done? All of it done? Perfect. Now look at the question what I'm showing you right now. Look at the question. A beam is there which is fixed at both the ends, but they are connected in series. Now the torque has been applied something like this, T0. Where the torque will be going? The torque will be going something like this. Yes or no, guys? When you just rotate it like this, try to imagine the 3D figure. Try to imagine the 3D figure. Rotate your finger, right hand finger in the anti-clockwise direction. Your thumb will be going what? In the rightward. At the point A, at the point B, at the point C. 3 points I'm going to consider, my dear friend. Suppose reaction torque will be something like this. Reaction torque will be something like this. You know that RA plus RC will be what? T naught. Yes or no, guys? Now this bar has been fixed at both the ends. So what is the total angle of twist? 0 or not? Theta AB plus theta BC will be 0. What about torque in AB section? Can I say minus RA? What is the torque in BC section? Can I say minus RA plus T naught? Check it out. Totally. Just try to represent this diagram with the what? Twisting loading diagram, and try to see with respect to what? Axial loading conditions. But there I have told you that whenever any load is moving away from the cross section, it is positive, but here it should be negative. That's the only difference is there in the sign convention. Check it out. All of you, please check it out. Check it out, guys. Yes or no? Tell me, guys, fast. I need to cover the syllabus today itself. Today is the last class. See, in this section XX is there. Torque in this AB section will be something like this or not? And whenever the torque is moving away from the section, according to sign convention, I've already mentioned that torque in this section will be minus T. Minus T means what? Reaction torque. Let me represent it by reaction torque. Otherwise, you will be confused. You will be confused. Let me just show by TA only. TA, TC. TA, TC. TA, TC. Check it out. For this one, my dear friend, and this cross section, if I just take the cross section in the BC member, T naught, TA is moving away, T naught is moving inside. It's a TA minus TA plus T naught. Check it out. Are you able to follow me sign convention or not? This sign convention. Representing the loading condition from the twisting. It is a twisting loading diagram. We are representing by double arrow, not single arrow, double arrow. That's the method actually. When you are moving from the left hand like this, whenever you used to find like this, you keep it as negative. Whenever you are moving like this from the left hand, and whenever you find like this, keep it as positive. Whenever you are moving from this hand, at any particular cross section, the load has been shown something like this, will be negative. Whenever it is TAB is having T only, right? Check it out. TAB is having T only. Check it out. Why T naught will be there? Check it out. First tell me, why T naught will be there? Where you just take the cross section, we are looking from this left hand, we are just moving from the left hand. Why T naught will be coming? T naught will be coming at the point B. When you take in between section BC, then T naught will be coming. That T naught will be seen. Left side, I already mentioned, my dear friend, starting from shear force, starting from bending moment, starting from axial loading condition, see from one side, not both the side at a time, either from left side or from the left side, right side. Or if you just see from the right side, TC minus T naught. That is also TAB. Not believing, check it out. TC minus T naught will be minus TA from here. TC minus T naught will be minus TA. Yeah. So always look at from only in one direction, either left direction or right direction. Do not basically combine both the direction at a time. Otherwise, you will get the wrong results. Now, once you got this thing, total deflection will be 0. Total angular deflection, angular twist will be 0 for both the shafts. So what will happen? Put the value, theta value. What is the theta value? What is the theta formula? TL divided by what? GJ. Sir, how? Here torque is given, length is given, J is given, G is given. From torsion equation, T by J, tau by R, G theta by L. Forget about this, equate these two. you will be getting what? This value. Because there is no role of tau. Because there is no role of tau. So that's why theta will be TL divided by GJ. Now, what is the T? TAB, LAB, GAB, JAB plus TBC, LB. Similar kind of thing that what we did in the what? Axial loading condition. Nothing much is there. TAB is what? Minus of T naught. TAB is what? Minus of T naught. TBC is what? Minus of TA plus T naught. Length has been given to you what? L by 4. Length has been given to what? 3L by 4. J is what? Same. J is what? Same. Because both are made up of what? Solid shaft D. So J and J will cancel out. G will also be cancelled out. So you will be left with the what? Minus T naught into L by 4 plus minus TA plus T naught into 3L by 4. That is equal to 0. So overall, what you will be calculating? Overall, what you will be calculating, my dear friend? Just tell me the TA value in terms of T naught. Just tell me TA value in terms of T naught. Quickly, guys, quickly. Sorry, just wait. Just tell me the TA value in terms of T naught. What will be the reaction torque in the left support? What will be the reaction torque at the left support? Quickly, guys, quickly. Let me calculate. This will cancel out. So it will be 2 by 4 into T naught. That is 3 T naught TA by 4. TA will be 2 T naught by 3. So TA I am calculating as 2 by 3 times of T naught. Check it out. 2 by 3 times of T naught. Now, once we got to know this thing, what will be the next segment? What will be the next segment? What about TC? What about TC? T naught by 3. Now tell me maximum torque. Either you are getting in TAB or TBC. In which member you are getting calculating the maximum torque? Tell me, guys. What will be the maximum torque? What will be the maximum torque? Can I say 2 by 3 times of T naught? Can I say 2 by 3 times of T naught? Perfect. Perfect. So maximum torque will be, maximum shear stress will be 16 times of T maximum divided by pi d q. Put the value, get the answer. Put the value, get the answer. Anything mistake we did? Any mistake we committed? Check it out in the calculation of this TA calculation. In TA calculation, check it out. It's a TA value. It's a TA. It's a TA. It's a TA. It's a TA. It's a TA, my dear friend. So what will be the answer? What is gonna be answer? 3 by 4 times of T naught. TA will be, T maximum will be 3 by 4 times of T naught. Once you know this thing, you can calculate 16T divided by pi dq. That is 3 by 4 times of T naught. Check it out. All of you, please check it out. All of you understanding my point? Check it out, guys. Quickly. Please check it out. Done? Done? Do not confuse with the maximum torque that has been attained. Do not say T naught. It's a 3 by 4 times of T naught. Right? I have told you about the shear force diagram. In that, you got to know W by 2 is a maximum shear force. Actually, looking at the figure, simply supported beam, W is acting, but W is not the maximum shear force. W by 2 is a maximum shear force when you just draw the shear force diagram. Similarly, when you draw the twisting moment diagram, you will never find maximum twisting moment to be T naught. You will always find maximum in among all length of the beam, whole length of the beam, you will find what? Maximum torque to be what? 3 by 4 times of T naught. Right? Getting my point? Perfect. Note down thin cylindrical and spherical pressure vessels. One of the very easy chapter. We can quickly wrap up. Thin cylindrical pressure vessel. What do you understand by thin cylindrical pressure vessel? And why we need this one? Why we need thin cylindrical pressure vessel? Why we need cylindrical safe container or spherical safe container? What's the need of this? To carry the high pressure fluid, right? To carry the high pressure fluids. Understanding or not? So one of the important point is that whatever the fluid has been stored, that has been stored at a very, very high pressure. Pressure is going to be very, very high. When the pressure is going to be very, very high, the chances of bursting will also be very, very high. Yes or no, guys? The chances for damaging the cylinder wall will be also be very, very high. So cylinder may fail like this, or cylinder may fail like this. Let me show that. Check it out. If I just talk about the thin cylindrical pressure vessel, it can be failed in two ways. Either the failure can happen by circumferentially like this, or the failure can happen when it is applying the loading condition like this. Check it out. Longitudinal it can fail. It can split into two cylinder, or it can split into what? Two particular halves. Check it out. All of you can imagine. All of you can imagine the failure or the bursting. Please note down the figure, very, very important. Please note down the figures. Once the figure will be completed, remember that the failure will happen in two ways. One is circumferential way, and the second is what? Longitudinal way. Longitudinal way. This is called circumferential failure. Circumferential failure. This is called longitudinal failure. This is called longitudinal failure. Very, very important. Now, once it is done, let me know. You can simply draw the figure. Do not draw to the exact scale. Done, guys? Note on the first failure, circumferential failure. Because of the circumferential failure, there will be circumferential stress will be developed. That we call sigma C. We also call hoop stress. Circumferential stress we also call hoop stress. How the failure will happen, my different? Try to look at very carefully. Try to look at the very carefully this particularly diagram which I am showing you right now. How the failure will happen. Now, if I just take the half portion of this one, you know that there is a bursting force that is going to be acting. There is a bursting force that going to be acting something like this. The pressure force will be acting all along this particular portion, but the bursting force will be acting. Resisting force will be acting like this. The resisting force is what? Green color. That is saving the life of the what? Pressure vessel. But whatever the red color which I am showing you right now, that is the bursting pressure because of the internal pressure, internal forces, because of the internal pressure of the what? Fluids. So what we can do for the safe condition, of this pressure vessel, at least this resisting force must be more than or equal to what? Bursting force. Who will be resisting? Who will be resisting? Hoop stress. And how it is acting? Sigma L will be L into what? Thickness. Check it out. L into thickness. In that portion only, see, whenever the material is there only the resistance will be there, right? Check it out. In hollow cylinder, my dear friend, in hollow cylinder to store the fluids, whenever the material is there, then only what we can have? The resistant force. But material is not there, how the resistance can be offered? Sigma H into L into T, but it is 2 times. Here, this is the portion of the resisting, this is the portion of the resisting. That will be equal to bursting force. Who is bursting? Pressure. Pressure into P into what? Length into diameter. In that particular area, the pressure is what? Exerting like anything. The pressure is going to be exerting like anything. So from here, what you can calculate the hoop stress from here. Hoop stress will be PD divided by 2T. Note down, hoop stress will be PD divided by what? 2T, my dear friend. Please note down, very, very important. That's a very, 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 very important formula. Done? Yeah. So you can just note down from here, hoop stress. Note down the longitudinal stress. When the failure is happening along the length of the cylinder, how the failure on resisting force will be developed on the cross section of the member? Let me show that. This is what the material we have. This is what the material we are going to have. Now try to understand and look at very carefully. Whenever we have the material, there only the resisting force will be developed. But you know that the pressure is going to be acting whole length. On this particular cross section, the bursting force will be acting. So your resisting force must be more than the bursting force. And you know that the resisting force will be what? Longitudinal stress into what? On what area it is acting? Can I say pi d into t? Can I say on pi dt area, that is that area for which the resistance has been offered by the material? That must be equal to bursting force. Bursting force is what? P into pi by 4 d square. Check it out. So from here, what will be the longitudinal stress? PD divided by 40. You can also write hoop stress is equal to 2 times of longitudinal stress. No, guys, very, very important. T is nothing but thickness of the cylinder. Thickness of cylinder. Very, very important. Please note it down very carefully. Thickness of cylinder. Once it is done, let me know. How you classify anything with thin cylinder or thick cylinder, sir? When you can classify the thin cylinder and thick cylinder? When you say any pressure vessel to be thin or thick. Now, once it is done, let me know. Once it is done, let me know. Done? Is it done? Perfect. So you can define pressure vessel to be two types: thin pressure vessel and thick pressure vessel. Whenever you say this internal diameter to thickness is more than or equal to 20, then you say it's a thin pressure vessel, because in this case the diameter is very, 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 very high as compared to the thickness, such a way that thickness can be negligible. In thick, it's not like that. So I can just show you by the representation. So this is a thin and this is thick. You can just imagine that the thickness is what? Very, very high. Check it out. The thickness is very, very high. But here thickness is very, very low, right? Yes or no, guys? With this particular ratio, you can just classify thin and thick pressure vessel. But remember, D is what? Internal diameter, not outside diameter. Not outside diameter. Now, note down the next thing, next concept, the changes in the dimension of the thin cylindrical cell due to internal pressure. What will be the strain value? What will be the strain value? That is what we need to calculate, my dear friend. What will be the longitudinal strain? What will be the hoop strain? What will be the hoop strain? Can I write like this? The state of a stress in a cylindrical material will be shown something like this: hoop strain, hoop stress, and longitudinal stress. So you know that the longitudinal strain, how to calculate? I know I told you the formula, right, in the first chapter. When the material is subjected to combined loading condition in the both the directions or in all the three directions, then this will be the case. Of course, in this direction we don't have any stress value. That's why there's no with minus something 0. So how you can calculate the hoop strain? PD divided by what? 2TE. Remember, D is the internal diameter. D is what? Internal diameter. Do not think of outside diameter, please. PD divided by what? 4TE. So now when you simplify, you will be calculating this hoop strain to be what? Hoop strain to be change in the diameter by original diameter, and that is going to be equal to PD divided by 4TE 1 minus 2 minus mu. Very, very important. Similarly, you can calculate the longitudinal strain also. That is change in length by original length. That is PD divided by 4TE 1 minus 2 mu. Note down, guys. Very important. One of the very, very important. This formula is very important, and this formula. How to calculate the volumetric strain? You know that the volumetric strain will be 2 times of hoop strain plus 1 times of longitudinal strain. So how? In the first chapter, I told you volume is what? Pi by 4 d square into L. Change in the volume will be what? Pi by 4 d square into what? Delta L. First time differentiation with respect to L. Second time differentiation will be with respect to what? Diameter. Divided by volume, you will be calculating what? This particular formula. Check it out. Right? Now, once it is done, let me know. Done, all of you? Done? Perfect. Perfect. Now, so volumetric strain will be change in volume by original volume. Note down directly the formula. No rocket science. No rocket science. Believe me, you can just get it by volumetric strain formula, something like this. Put the value of this one, put the value of this one. You will be calculating this formula as like this. Now, once it is done, let me know. We can discuss about the thin cylindrical pressure vessel. Sorry, cylindrical pressure vessel has been discussed. Now we need to discuss about thin spherical sail. Thin spherical sail. Now, thin spherical sail, there is some specialty. There was a diameter and length, but now it is just like a symmetric one. So whatever the hoop stress will be there, that is equal to what? Longitudinal stress. There will not be that much difference. So both are going to be have the same formula. Not only formula, PD divided by 40. Hoop stress and longitudinal stress formula will be PD divided by 40, my dear friend. All the things will be equal. How? Check it out. Internal pressure bursting will be there like this. So whatever the pressure force because of this will be what? P into pi by 4 d square, and the resisting area of course will be same. Whatever the resisting area will be there, that is going to be same. That has been offered by the thickness of the tube, like pi dt, and that you are going to get what? PD divided by 40. So here, if I just take any point and if I draw the state of stress, it will be sigma, 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 sigma. Yes or no, guys? Because all are equal. So please note down this thing, very, very important. Once it is done, let me know. So I will extend the class by 10 minutes because I need to finish the columns also, so that we can finish our course of this form today itself. Theories of failure will be covered in the machine design, right? Compressible fluid flow, that I will discuss. After fluid mechanics, you just have one more particular small portion that has been added recently, gate examination. In fact, in many PSU, they are asking the question also from the compressible fluid flow. Compressible flow rather than we can say. So for understanding those topics, you must understand what is the meaning of incompressible flow and what is the meaning of incompressible fluid. Again, you must understand what is the meaning of compressible fluid and compressible flow. Fluid and flow both are different things that we are going to discuss in detail. And what will be the respective formula, that will also be we are going to see. Not done, all of you? Is it done? All of it done? Check it out and let me know as quickly as possible. Yes. Perfect. Thank you. Change in diameter and volume of the thin spherical pressure vessel. What will be the change in volume and other thing that we need to calculate? So again, that is a very simple thing. I told you I just already told you hoop strength will be PD divided by 4T E minus P into mu into PD divided by 4T. So hoop strength will be equal to longitudinal strain, and that is going to be equal to what? PD divided by 4Te 1 minus mu, right? Volumetric strain will be 3 times of hoop strain. So that is what? 3 into PD divided by 4Te 1 minus mu. Check it out. All of you, please check it out. Mu is nothing but Poisson ratio. Poisson ratio. Done. Once it is done, let me know. Perfectly fine. Now, so all of you are comfortable if I extend the class by 10 to 15 minutes, right? There's no problem, right? Okay. Yeah, thank you all. Now try to understand. See, a spherical steel pressure vessel of 400 mm diameter with the wall thickness 20 mm is coated with a brittle layer that cracks when the strain exceeds the 100 into 10 power minus 7. What is the internal pressure that will cause the layer to develop the cracks? That is a very good question and very simple and straightforward. All of you, please try it for 1 minute. Now, see the solution, guys. It's a very easy question. Very easy question. They coated with the material and strain value, not volumetric strain, it's a strain value. When they mention it's nothing but only strain, hoop strain or longitudinal strain, both are same thing. And that is equal to what? PD divided by 4TE 1 minus mu, right? That has been given 100 to 10 power minus 7. Pressure value we need to calculate. Wall diameter is 400 mm. 400 mm. Thickness is what? 20 mm. E is what? 200 gigapascal. Convert in megapascal, something like this. 1 minus 0.3. Straightforward. If you just calculate, you will be getting the answer as 0.57. All of you, please check it out. Done. Done, all of you? Now try to solve this question and let me know the answer. Question number 2 for this thin cylindrical pressure vessel and the other stuff. Take your time for 1 minute and let me know the answer. That has been asked in Engineering Services Examination 2019. Engineering Services 2019 examination, they have been asked this question. A spherical cell of 1.2 meter internal diameter is filled with the water. Filling with the water has been done until the volume is increased by this much of volume. And Young's modulus, they have given Poisson ratio, they have given neglecting the radial stress. They are asking hoop stress developed in the cell. Hoop stress developed in the cell will be nearly. So from here you can just calculate, volumetric strain, that is change in volume by original volume. That has been given as 400 into 10 power 3 divided by volume. Volume is what? You know that. Everybody know that. 4 by 3 pi r cube. From here you can just calculate the volumetric strain. Once you calculate the volumetric strain, you know that the volumetric strain is what? 3 times of hoop strain. From here you can just calculate the hoop strain. Once you get the hoop strain, you know that the formula for hoop strain, that is sigma h divided by E 1 minus mu, right? So from here, my dear friend, you can just calculate what? Hoop stress. Understanding my point? Answer will be A. All of you are getting my point or not? The procedure which I am telling you right now. But important thing is that to getting the answer, you must be very sharp in the calculation, very fast in calculation in between these steps. Otherwise, it will exceed 1 minute. Understanding? Done. Shall we start our discussion on the columns? Very small topic, right? But very important, because many times in examination they are asking. In fact, in the PSU examination. Tell me, guys, if it is done, let me know. Done? Is it done? Done, all of you? Yes. Note down columns and struts. Column is basically a vertical member. Column is basically a vertical member which is being subjected to, note down the definition. A column is nothing but a vertical structure member which is subjected to axial compressive load. Remember, not tensile load, axial compressive load. Please note down. Columns defined as a vertical structural member, subjected to axial compressive load during its functionality. Very, very important. So we have basically 3 types of column: long column, short column, and then we have medium column. Note on whatever the things I have written on these slides. Whenever you apply the compressive load, it will try to buckle like this. It will try to buckle, this beam will try to buckle like this. If it is a long column, right? So note down, it will, long column failed by buckling. Long columns generally fails by buckling. Short columns, whenever it is short, then it is failed by crushing. Right? Medium column fails by both. That means crushing as well as buckling both. Crushing as well as buckling both. Note all these things. Now long column, they are very, very strong in crushing. Short column, they are very, very strong in buckling. When the length is very, very high, take a very, very long pen. You try to apply the compressive load, it will fail, buckle. Laterally, it will buckle. But if you just take this short chalk piece, you try to apply the compressive load, it will never fail. Now, so we have the method for long columns. That is nothing but Euler buckling theorem we have. Like you have the torsion theorem, Bernoulli's theorem for bending, right? A lot of theorems has been proposed. So for columns also, Euler has been proposed one theorem. Remember, whatever the formula we are going to discuss in this chapter, only valid for long columns. Once it is done, let me know. Just 5 minutes more I will take, not more than that. Done. Note down Euler formula for this one. What is the amount of maximum load, buckling load we can apply? That buckling load we call Euler load. And what is the formula? Pi square EI minimum divided by LE square, where L is nothing but equivalent or effective length of the column, where L is nothing but L into alpha. Alpha is nothing but, note down what is the meaning of alpha? Length of fixity coefficient. Length of fixity coefficient. It will depend on the end conditions. It will depend on the end condition. It will depend on the end condition of the columns. How the columns has been basically subjected to the supports, whether it is a hinge support, fixed support, free support, or nothing is there, right? Pin support or what? I minimum is what? Suppose you are taking any column and the cross section of this column is what? Rectangular. Then suppose you are applying the compressive load, then you will be calculating Ixx and Iyy. Among all, whatever the minimum is there, that you're gonna take as in this formula. That's why we are adding pi square E I minimum divided by LE square. So this is called Euler's formula or equivalent length of a column. Now, once it is done, let me know. Done. Remember, this formula is valid for this theory or this formula. This theory has been proposed for long columns only. It is not for the short, it is not for the medium columns, because they are not going to be failed. They are not going to be effectively failed by buckling. That's the reason. Now done. Is it done, guys? Perfect. So note down some conditions of alpha. Note down some conditions of alpha value, when both the ends are hinged one. When both are hinged, alpha will be equal to 1. When one end is fixed and other end is free, then alpha is what? Then alpha is what? 2. This is nothing but length of the column. When one end is fixed one and other is end is what? Hinged one. Then what will be the values of alpha? Alpha will be 1 upon root 2. When one end is pinned one, but other is what? It's free. Or we can say, both the ends are basically what? Just wait. Just note on the table column which I'm showing you right now. Fourth condition I'm telling you. Just wait. Fourth condition I'm telling you, when both the ends are fixed one. What is happening? That is getting stuck. All of you can able to see my screen? Just wait. Hello, hello, I'm audible. Just wait, guys. Actually, my system is actually getting stuck. Just wait. Yeah, just wait, just wait. Yeah, getting responses positively. Perfect. Now, so I was telling you the fourth condition that I want to show. When the ends of the beams are ends of the columns are fixed one, then alpha will be what? 1/2, right? So here LE is equal to what? Alpha times of L. Alpha times of small l. So alpha is what? For this case, alpha is equal to 1. For this case, alpha is equal to 2. For this case, alpha will be 1/2 and alpha will be 1/√2. Yes or no, guys? And accordingly, formula will also change, right? Yes or no? Crippling load or Euler load, both are same thing. Sorry. But it's a very important. I is what? I minimum. I minimum. If it is a circular cross section, we do not worry about that much. But if it is a rectangular cross section, a non-circular cross section, then we have the difficulty. Among IXX and IYY, we need to choose the minimum one, least one. Now, once it is done, let me know. So it is a fixed one. Done. Can I move to the next one? So vertical column, we have the two moment of inertia, IXX and IYY. And among that, we need to choose minimum. Why minimum? Because column will tend to buckle in the direction of least moment of inertia. B. See, when larger and larger moment of inertia, larger and larger will be the resistance. You know that the moment of inertia is what? Inertia only, one kind of resistance only. The lesser the resistance, the attack will be more there itself. Yes or no, guys? Note down the last one, cylinderness ratio. It is defined as effective length of the it is defined by the one basically symbol as effective length of the column. It is a ratio of the effective length of the column to the least radius of gyration, to the least radius of gyration. LE divided by K. What is the K? I, you know that area into K square, where K is nothing but what? Radius of gyration. I divided by area. Yes or no, guys? Yes or no, guys? K is nothing but a radius of gyration. Least radius of gyration. Please note down. Where K is nothing but I minimum divided by area. Very, very important. So, put down for short column, cylinderness ratio less than 30. Then we say it's a short column. For long columns, cylinderness ratio will be more than 100. For medium columns, cylinderness ratio will be more than 30 and less than 100. More than 30 and less than 100. That is called medium columns. Means sometimes short column, whether column to be called short column, long column, or medium column, sometimes it is not defined by the length. Sometimes it is defined by cylinderness ratio. Right? Understanding my point? Is it done, all of you? Done. What do you physically mean by the slenderness ratio? What do you mean by the slenderness ratio? When slenderness ratio will increase, the chances of buckling will increase or decrease? It's a very simple. When slenderness ratio will increase, the chances of buckling will also increase. Check it out. For long column, slenderness ratio is what? Very, very high. That means the chances of buckling will also be very, very high. But sir, this you are telling based on the what the thing you have mentioned in the particular slides. But I'm not understanding physically. So let me just explain you just for 2 minutes, 2 more minutes. Once it is done, let me know, guys. See, because of the loading, axial loading, because of the compressive load, stress will be developed. What is the stress? Crippling load or Euler load divided by area. What is the crippling load or area we can say? Tell me, guys. What is the crippling load? Can I say pi square EI minimum divided by LE square into A? Sir, what is the A? Now, what is the I minimum by A? Can I say K square? Now, can I say pi square EI divided by LE square? LE by K is nothing but S square. Check it out. All of you, please check it out. Whatever the Euler stress will be there, that is pi square E divided by S square. For a given area and for a given material, for a given area, for the given Young's modulus, sigma E is what? Inversely proportional to slenderness ratio. When it is very, very high, then what will happen? No, just wait. For the given area, no, try to compare. Try to compare this one. Try to compare this thing with this one. So PE divided by A will be pi square E divided by what? S square. So for the given area, and for the given material, P is what? Inversely proportional to S square. Check it out. Euler buckling load will be inversely proportional to S square. Check it out. Yes or no, guys? When slenderness ratio will decrease, actually, see, try to think in this way. When slenderness ratio will decrease, when it will decrease, Euler buckling load will increase. That means the column is going to have more tendency to bear the amount of compressive load. Check it out. P is nothing but whatever the load that we are able to apply on that column, so that buckling will not happen. When slenderness ratio is going to be decreased, when it will decrease, then P is going to be increased. That means what? The column is going to be have the larger bearing capacity. That means buckling tendency will decrease. Understanding in this way? Buckling tendency will decrease. Suppose S will increase, then the P will decrease. That means amount of load that can be carried by the columns will decrease. That means chances of buckling is going to be increased. Yes or no, right? Because what is the meaning of P to be smaller and lesser? That means P is smaller and smaller. That means the moment you are going to apply larger amount of compressive load, it is going to buckle. Understanding in this way? Tell me, guys. Just think in that way practically. If slenderness ratio will decrease, then amount of load that can be carried by this column, buckling load, that is the Euler load, that is PE, will also be increased. That means larger amount of load that you can apply, but buckling will not happen. That means buckling tendency will decrease, right? So note down very, very important points. But area must be same. In both the conditions, area must be same and Young's modulus or material must be same. If you change the material and suppose you increase the load, it doesn't guarantee that whether the same phenomena, whether the buckling will happen or not, that depends on the material, because you change the material. I'm saying for same material, so that the Young's modulus will also be same and area will also be same, right? So that's a condition actually. So now once it is done, we have the 2 to 3 numerical, I think 1 or 2 numerical, that after that we can close this session, right? Done. Is it done? Perfect. So try to solve this one and let me know the answer as quickly as possible. If the diameter of the long column is reduced by 20%, that means d2 minus d1 by d1 is what? d2 is what? 0.8 times of d1 now. Final diameter is basically reduced by 20%. That means 80% the initial diameter. They are asking what will be the Euler buckling load. The reduction in the Euler buckling load will be they are asking this thing. You know that P is what? Directly proportional to what? What is the formula? Pi square E I minimum divided by L square. I is what? Pi d power 4 by 64. What is the I for circular cross section? Pi d power 4 by 64. Remember, I'm talking about Ixx, I'm talking about Iyy, not polar moment of inertia. Polar moment of inertia will always will be useful in the what? Twisting, not in the axial loading conditions. So it is inversely proportional to d to the power 4. So simply d1 by d2 to the power 4 minus 1 into 100. So it is going to be what? 1 upon 8 to the power 4 minus 1 into 100. Now tell me the answer as quickly as possible. Sorry, not inversely. It is directly proportional, right? It is directly proportional, right? Yes or no, guys? The Euler buckling load is directly proportional, right? So 0.8 to the power 4 minus 1 into 100. So that is going to be 59. That will be the answer. Minus sign means reduction. Note down fast. So Euler formula holds good for long column only. Now for both short column, long column, what we have? We have Rankines formula. We have Rankines formula where we are considering both crushing load and Euler load together. And we are calculating one resultant load, right? That is not there in the, basically, of course, it is there in the GATE syllabus, but right now for PSU examination, we are not focusing. Now, note on the last problem and let me know the answer. Take your time. A column has a rectangular cross section, 10 mm, 20 mm. Length is 1 meter. We can also say 1000 mm. The slenderness ratio they are asking, that means LE divided by K they are asking. Simply L divided by K. Nothing has been mentioned. Alpha we cannot calculate. Simply you take both the ends hinged only, right? So LE will become what? L by K. L by K is what? I minimum by area. That will be the answer. Now what will be the I minimum? You just calculate Ixx first of all. That is 10 into 20 cube divided by 12. Then you calculate Iyy, 20 into 10 cube divided by 12. Among all, whichever is the minimum, that you take it out to be I minimum. So S is what? L is 1000. Moment of inertia, you got to know, that is 20 into 10 cube by 12. By area is what? 10 by 20. That is 25 by 3. Just take the under root. Just divide by 1000. 346 will be the answer. See, slenderness ratio, so there will not be any unit, right? Because L is what? Meter. K is what? Also meter. Because I is what? Meter power 4 by meter square. Sorry. I by A means what? Meter power 4 by meter square. This is nothing but meter square, and under root of that means what? Meter only, right? So that's all, my dear friend, regarding strength of material. Theories of failure will be covered by basically what? In the machine design course only. And maybe I will meet you on 19th or 20th of this month by the subject called, with the subject called compressible fluid flow, right? And try to practice as hard as possible, my dear friend, with respect to all the subject, whatever the subject has been finishing, right? Understanding or not? So, okay, guys, thank you. And, whatever the doubts you have, just let me know in the WhatsApp. ES paper. Yeah, objective, that one, right? Objective PDF you want to say, right? Where we have the all previous year paper. Yeah, I will just let you know. Just ping me on WhatsApp. I will just find it and send you, right? You can just ping me on group, or maybe you can just directly message me also. No problem. So okay, yes, thank you, right? Yeah.